Hello and welcome. Today we're going to cover all the incredible tools and features available in Ometa Flow. At Ometa, we care about the small molecules that make up our medicines, food, cosmetics, clothing, and ourselves. These small molecules, or metabolites, are essential to life as we know it. While you may be familiar with some of these metabolites, we've likely only identified a small fraction of the metabolites that exist in our world. These small molecules have the potential to be the next groundbreaking medicine or the next environmental threat. So, how do we discover these unknowns? Mass spectrometry-based small molecule metabolomics is an incredibly powerful tool for identifying and discovering new metabolites. A single untargeted metabolomics experiment can identify tens of thousands of metabolites in a single sample. But actually figuring out what those metabolites are can be very difficult and is usually the biggest hurdle to using this data well. That's where we come in. Ometa Flow is a data analysis ecosystem that can analyze, annotate, network, search, discover, and share small molecule mass spectrometry data. Our server-based software means that all data and analyses are stored in one secure location that can be easily accessed from anywhere. Every analysis task on this server is assigned its own unique ID, which can be securely shared across your organization and used to exactly reproduce previous analyses. Data analysis in Ometa Flow is organized into over 50 workflows that cover processes such as data cleaning, spectral library creation, library searching and compound annotation, molecular networking, mass spectrometry search algorithms, statistical analysis, and more. For example, our targeted analysis workflows allow users to upload a list of compound masses, structures, or formulas, and automatically find those compounds, and their adducts, in mass spectrometry data. Our untargeted analysis workflows can take mass spectrometry data without any pre-processing and generate metabolic features, search against spectral libraries, integrate peak areas, and generate molecular networks to propagate feature annotations and identify unknown molecules. So how does this work? Let's say you want to perform an experiment to discover all the potential metabolites of the drug as a... First, you'll collect samples under many different conditions and run them on your mass spectrometer. That mass spectrometer will then give you MS1 spectra with the mass and retention time of the metabolites in your sample. This information can be used to predict the chemical formula of your compound and provide its relative abundance and retention time. However, while important, this information is often not enough to identify your metabolites of interest. That's because many compounds have exactly the same chemical formulas, even if they have very different structures and functions. So, in MS-MS experiments, we run an additional round of mass spectrometry called MS2. In this round, instead of measuring the mass of the entire compound, we will split that compound up into fragments and measure the mass of those fragments. This creates a chemical barcode that provides information on the chemical substructures within the molecule. These barcodes can then be used to identify metabolites. How this happens in real life is through a process called library annotation. In this process, we compare our experimental MS2 spectrum with spectral libraries containing MS2 spectra from known compounds. We use an algorithm that compares the mass and intensity of the MS2 peaks to find the library spectrum that best matches our experimental spectrum. Here's an example of what this looks like. At the top, we're matching the experimental spectrum of sucrose to the library spectrum of sucrose. The algorithm we're using to do the matching is called a cosine score, where the best score is 1 and the worst score is 0. As you can see, this is a very good match, so our cosine score is 1. However, if you then try to match the experimental spectrum of sucrose to the library spectrum of a different compound, say azithromycin, you'll see this match is not very good, and so we have a cosine score close to 0. Now, Ometa Flow comes with all commercially available libraries from the public repositories GNPS, MassBank, and MONA, which currently contain almost 1 million library spectra. However, we also have tools to import and manage your own custom libraries, including high-throughput tools to extract library spectra from mass spectrometry files. This is great when you're studying common metabolites where library spectra have already been collected. However, what happens when you're looking for novel compounds or working in a system that's not very well studied? What happens when there are no library matches? This is actually a very common problem. On average, only about 15% of metabolites in a typical untargeted metabolomics experiment are annotated using library matching to our best-in-class public libraries. Now, this number may get up to 25 or 30% if you're working with human samples, but that still leaves the majority of your metabolites unannotated and undiscovered. This is where molecular networking comes in. Instead of just performing the library annotation step, where experimental spectra are compared to library spectra, molecular networking performs an additional step, comparing experimental spectra to each other. And since MS2 spectra give us information on the chemical substructures within a molecule, compounds that have similar MS2 spectra tend to have similar structures as well. Thus, molecular networking can identify structurally related metabolites, whether they have a library match or not. What this ends up looking like is that each metabolite will be represented as a circle, or a node, and if two metabolites are similar enough, there will be an edge between those nodes. Applying this to an entire experiment generates a molecular network. Molecular networks organize into subnetworks, which typically correspond to specific molecular families. Within subnetworks, you'll have compounds that have or don't have library matches, but for those metabolites that don't have library matches, you now have a whole list of compounds that are structurally related to your unknown metabolite of interest. Here's an example of how this works. This is a subnetwork in which all the compounds with library matches are different bile acids, so it's not too much of a leap to hypothesize that your unknown metabolite is also going to be a bile acid. Molecular networking can be combined with sample metadata to provide important context for identifying novel compounds. For instance, bioactivity data can be layered over the network to identify bioactive metabolites. We also provide workflows to detect adducts in the network, add new data to an existing network, and identify library compounds that are similar but not identical to unknown metabolites. We also provide several algorithms to perform networking and feature selection. Each of these algorithms has its own strengths and weaknesses, which is why we make it easy to run different algorithms and compare results. Molecular networking can be incredibly powerful, but it's not going to answer every question you have about your data. One of the most common questions we run into is, have we ever seen this metabolite before? The mass spectrometry search tool, or MAST, can answer this question by searching billions of MS2 spectra in seconds. It will then return every sample where your compound has ever been detected, as well as any analogs of your compound. MAST can also retrieve metadata and sample information from every match. This tool becomes incredibly powerful when paired with custom databases. Enriching MAST results with rich sample metadata can allow you to track novel compounds through manufacturing lines, waterways, taxonomic distributions, or time without having to first identify that metabolite. This can be a great way to find new sources of potential lead compounds or prioritize novel compounds for further study. While MAST uses MS2 spectra to find matches, the mass spec query language, or MassQL, allows you to perform flexible searches of mass spectrometry data for specific chemical classes, substructures, neutral losses, retention times, charges, isotope abundance, etc. This powerful and flexible search tool can be used on raw mass spectrometry data or within a network to identify compounds of interest using their unique spectral features. All of these tools are integrated into our robust data ecosystem that is committed to making all data and analyses findable, accessible, interoperable, and reusable. Ometa Flow uses open source file formats, which allows you to analyze and compare mass spectrometry data no matter what instrument it was collected on. Every experiment, file, and individual spectra within Ometa Flow is assigned its own unique ID, and each analysis task has a unique permanent URL that can be easily shared within an organization. Parameters for every analysis are reported and can be exactly reproduced using a single click. And finally, all data and analyses are stored on a central server, which allows users to securely access results from anywhere. So what can you do with Ometa Flow? You can use it to identify novel drug metabolites, without any prior knowledge of all the potential biotransformations of that drug. Molecular networking can identify metabolites that are structurally related to your target drug, while downstream statistical analysis can pinpoint which of those metabolites are upregulated under certain conditions. MassQL can be used to rapidly identify novel flavonoids by searching for specific chemical substructures that are shared by flavonoid classes. Ometa can be used to perform quality control analyses across product batches to identify novel contaminants, measure their differences between batches, and even track the source of contamination. The tools available through Ometa Flow are already used across industry and academia in the fields of agriculture, food chemistry, drug discovery, natural products, cosmetics and textiles, environmental monitoring, and many more. Check out the links below for more cool applications of our tools. That was a brief overview of all the great tools available in Ometa Flow. As always, if you have any questions, feel free to reach out using the link below. Thanks for watching.